Hey guys, this is Mr. Oliver. I'm going to go over the solution for AP Physics 2, Unit 5 for response question number 1. So let's go and get to it. Okay, so this first question is your classic mass spectrometer problem. And we did some examples like this and a couple of daily physics problems. So this should be no challenge for you. The first question, it says, explain why the particle moves through the parallel plates undeflected in terms of the forces exerted on the particle. All right, so during this region right here, we see that there's a charged particle moving through this magnetic field, but there's also some electrical plates here. So we want to explain what happens. Well, diagramming it out first is actually kind of nice to do. So if we look at it, this top plate, which is parallel to this bottom plate, is connected to a battery, and that battery has a positive end on top and a negative end on the bottom. So that means that the entire upper portion of this plate is positively charged. So the upper plate is positive, and the lower plate is negative. All right, so what that means is that you're going to have an electric field that points from the positive towards the negative during this entire region. Okay, so here's these electric field lines. They're uniform, constant during this entire time. And so my electric field points downwards. All right. Now, also, the magnetic field is present as well. And so during this case, that if I had to have a particle not be deflected, then I'd have to have a force that opposes the other one. So I don't know what the charge is, but let's just see what happens if this is a positive charge. So if this is a positive charge, I'm going to just draw it out here. I'm going to have an attraction towards the bottom side because this is negative, and a repulsion away from this top side. And so if you remember, for positive charges, you always have electric forces that go in the same direction as electric fields. So there's an electric force on this positive charge pointing down. So will the magnetic force oppose that? Well, the magnetic force depends on the direction of the field and the direction that this thing is moving. So it said that the particle is moving to the right with a speed v. So if I use my right hand rule, it's moving to the right. It's going into the page, so I can't get my hand that way, but it's going into the page. And so because it's a positively charged particle, there will be an electric force that goes up. And so sure enough, if you have these fields set up in the right orientation, the electric field produces a force down and the magnetic field produces a force up. And so therefore they cancel. And that means that that charged particle will move undeflected in terms of these two forces. The magnetic force and the electric field are equal and opposite reactions. Now, would it be true if it was negative? Well, sure, of course it would. Because if this was a negative charge, let's make this negative, it would be attracted up towards these positives. And so for this new scenario, you would have an electric force going up. And just remember, using the right-hand rule, if you have a negative charge, the forces flip around. And so the magnetic force goes down. And they'd be equal and opposite. All right, so that's question number A. Question B says, what is the sign of the charge on the particle? Well, you can't tell from this. It could be positive or negative. But if you look in the region to the right, over here, I'll just do it on this, that charged particle turns to the right. Okay, so that means that there had to have been a force, some kind of a magnetic force that pushed it down. Well, the only way for that to be true is if that charged particle moving to the right, exiting that thing, was negative. All right, so that charged particle must be negative in order to turn to the right. All right, so just remember that if you have magnetic field lines going into the page, okay, that's magnetic field into the page, and you have some random charged particle that enters that field, let's say it's coming over this way, if it turns that direction turns to the right, this is going to be a negative charge. Negative charges turn to the right with these inward facing magnetic fields. And if it turns to the left, that's going to be a positive charge. So that's just kind of a good thing to remember when you're dealing with magnetic forces. Question C refers to some more information. It tells us the magnetic field is 0.3 Tesla with a plate separation of 5e minus 3. So it tells us how far apart these are. Singly ionized particles, what does that mean, singly ionized? Singly ionized just means the charge is equal to plus 1.6 e minus 19 coulombs or negative 1.6 e minus 19 coulombs. That's a singly ionized. In other words, it lost or gained a single electron. All right, and so various speed particles are going to enter the region between the plates, and only the ones that have this particular speed are undeflected as they pass between the plates. These particles then reach the collector plate at a distance of 0.42 meters below the point at which they left the region. So that means that this distance here is 0.42 meters. So if this is the diameter, then the radius, which is important, is 0.21 meters. Okay. Question C. Based on your explanation in Part A, derive an algebraic expression for the potential difference that must be applied to produce the motion of the undeflected particles. Use that expression to calculate the numerical value of the potential difference. All right, so anytime I have some kind of a complicated setup, I'm always going to start with the basic facts of what we know. And what we know from Part A is that the electric force and the magnetic force are equal. All right, so we'll say that the electric force must equal the magnetic force. Okay. Well, the electric force is given by the charge times the electric field. The magnetic force is given by the charge times the velocity of the charge times the strength of the magnetic field. All right, so if you remember, we get this relationship that E is equal to the velocity times B. Now the question is, how do I get voltage? Well, if you look up here, I've got a parallel plate situation that produces this uniform field. And that's a special case where if you have that situation, the electric field is just the potential difference, delta V, divided by how far apart the plates are, which is D. So I can replace E with potential difference divided by that plate separation D. And that's going to equal the velocity times the magnetic field. All right? So the potential difference, delta capital V for voltage, is just V times B times D. All right? And so we're given the velocity, that's 2e to the 6. We're given the magnetic field, that's 0.3. And we're given the plate separation, that's 5e minus 3, which leads to calculating 3,000 volts for that voltage. So in order to make those particular particles go straight through, we need to make sure this power supply, our battery, is a 3,000 volt constant voltage. All right. Part D asks, by analyzing the circular part of the motion, derive an algebraic expression for the mass of the particles. Use that expression to calculate a numerical value for the mass. Okay. So once again, we've kind of done this already in the short answer practice, but F is equal to ma. That's where we start to derive anything. The force in this case is the magnetic force. The acceleration is a centripetal acceleration. So we'll make a substitution here. Magnetic force is Q times velocity times B. And on the right hand side, we get m times velocity squared over the radius, r. And so rearranging this equation, we can cancel one of the v's, and we got to multiply by the r, and then divide by the velocity, and we get mass by itself. So m, the mass, is qbr divided by the speed. And they tell us what the charge is. It's singly ionized, so it's 1.6 e minus 19. Magnetic field is 0.3. The radius was half the diameter, which was 0.21. And the speed we said was 2e to the 6 meters per second. So when we make this calculation, the mass is 5.04 times 10 to the minus 27 kilograms. All right. That's for part D. And then the last part states, a scientist wants to use the apparatus to separate singly ionized atoms of carbon-12 and carbon-14 in order to use the carbon-14 radioactive dating. Describe how the motion of the two isotopes of carbon in both regions of the apparatus leads to their separation, appropriately relating your description of the algebraic equations you wrote in C and D. Okay, so in C, let's just rewrite what we wrote in C. So for part C, this is what I wrote. Delta V is equal to V times B times D. Okay, so the voltage is equal to the velocity times the magnetic field times D. And then for part D, I wrote that the mass is equal to QBR divided by the speed. So these are two expressions. And it says, describe how the motion of the two isotopes of carbon leads to their separation, appropriately relating your description. Okay, so in order to have a particle that travels through the first part undeflected, we had to have a certain voltage. We had to have 3,000 volts. And so these particles are moving at a speed of v, right? So the velocity. Magnetic field is set, plate separation is set. So due to the masses of not being in this relationship, the fact that the heavier carbon-14 compared to the carbon-12 doesn't play into this initial part, we can say that that both particles are going to go through this as long as they both have the same velocity, same magnetic field, same D, same everything. So in the parallel plate part, we'll have no separation. Okay. According to our relationship in part C, the only difference between carbon-12 and carbon-14 is their mass. They're still singly ionized. Everything's the same. So that's not going to do anything for us. But in part D, we found out that the mass, depending on how this changes, will definitely change the radius of what those particles are going to have. So let me rearrange this equation. Radius is mv over qb. The charge doesn't matter because that's going to be the same for both of them. The magnetic field doesn't matter. That's going to be the same for both carbons. The velocity is going to be the same. So the only thing that's going to be different is going to be the mass. And so the more massive the particle, the bigger the radius. And so what you're going to see in that region, when those particles exit those parallel plates, the heavier, more massive particle is going to have a larger radius. And so they're going to hit way down here on this collector plate. That would be like the carbon-14. It's more massive. But the lighter weight carbon-12, this mass number is not going to be as big. And so when it comes out, it's going to hit closer to the exit point. And so then you can conclude that, oh, hey, these particles that are hitting closer are my carbon-12s. The heavier ones are going to be my carbon-14s. And so that's how you would use those two relationships to determine how to separate those two isotopes of carbon. All right. So, guys, that's the last part of question number 1. If you have any issues or you still have some questions, just shoot me an email. I'll be glad to help you out. Thanks a lot, guys, and have a good day.